Good morning, everybody. Hope all of you are well. Today I will continue the D block elements. Okay. In my previous class, I discussed about the electronic configuration. Today I shall discuss the general characteristics of D block elements. Okay. First, we will discuss about the melting point and boiling point. These D block elements are metals. They are called transition metals, and they have high melting point and boiling points. Okay, and these melting point and boiling points increases up to elements with 5 unpaired electrons. Okay, and then decreases. If we increase the number of unpaired electrons, definitely the covalent bonding will increase. Okay, as well as the metallic bond will be stronger and melting point will be higher. Manganese and technetium, they have abnormally low melting point. This is because of their highly stable D5S2 configuration. Okay, all 5 electrons are half filled in d orbital. Okay, so as this electronic configuration is stable, so their melting point is low and their covalent bond formation ability is low. And another case we can tell that zinc, cadmium, mercury, they have D10 systems. Okay, that means d orbitals are fully filled. So you know that fully filled electronic configuration. Okay, fully filled orbital electronic configuration very much stable. So here also no electron available for bonding amongst the atoms. Okay, of these elements. So these elements having very low melting point and boiling point. Next we will discuss about the metallic character. D block metals, okay, exhibits all the properties of metals such as electrical conductivity, thermal conductivity, metallic lusters, malleability, ductility, and these elements exhibits high enthalpies of atomization. Okay, you know that if any compound is there, if you want to separate the atom, then amount of energy required, that is called enthalpy of atomization. Okay, and metals with high enthalpy of atomization are generally noble metals, and these metals and the metals of the second and third transition series, okay, have greater enthalpy of atomization than the elements of the first transition series. Okay, and greater the number of unpaired d electrons, greater the number of bonds or covalent bonds, and hence greater is the strength of the bonds. If you think about that chromium, molybdenum, tungsten, okay, they are very hard as the number of unpaired electrons are highest, but if you think about zinc, cadmium, mercury, where complete pairing of d orbitals takes place, and they are not very hard because the absence of the covalent bonding, and this is why mercury is a liquid compound. Next we will go to the atomic radii. Atomic radii of transition elements decreases across the period as the nuclear charge increases from left to right in a periodic table, but here the decrease is in size is very less or small. This is because of the electrons in the d subcells has a less screening effect than the p and s. You know the screening effect decreases from s, p, d, f. F orbital has the lowest screening effect. Okay, and so the effective nuclear charge increases small. Okay, and the atomic radii decreases slightly. If we look at this scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, what we will observe that these atomic radii of elements towards the end of the series increases with increase in the atomic number. It is due to the increase in the force of repulsion added to the electron. So here you see that zinc, cadmium, mercury, here its value is high. Here you see it is decreasing. Okay, then again here it is increasing. This is because of electronic repulsion. And the atomic radii decreases up to manganese. Here you see 164, 147, 134, 127, 126. Then manganese and iron same, and cobalt decreases and nickel also decreases. Very slight, just 1 picometer only. Okay. The atomic radii decreases up to manganese, okay? And but from iron, the pairing of electrons in d orbital takes place and results in the electron-electron repulsion, and these lead to increase in the size. But the increase of nuclear charge try to decrease the size. In case of iron, these two factors balances each other, and so there will be no change from manganese to iron. So here you see manganese to iron. Actually, what is happening? The nuclear charge increases. Okay, so size should decrease. But as there is pairing of electrons, d6, one electron will be paired, and there will be repulsion. But these two are cancelling each other. Okay, and the size remains same. And here also you see the same. So the atomic radii increases. If we see the down the group, then the atomic radii of elements of second transition series are larger than the first transition series elements. But the atomic radii of third series are almost equal of those of the second transition series. This is because of the lanthanide conduction, which is because of the 4f orbital which must be filled before the 5d series of elements. Okay, and this decrease in the radii, addition of a new cell, okay, compensates, okay, each other. Hope you can understand what I am telling. Okay, and two things, okay, already I have discussed. That is the less scaling effect of the 4f orbital and increase of a new cell. Okay, they are compensate each other, and result is because of this lanthanide conduction is that the elements of the second and third series exhibit similarly. Here you see that I have shown that vanadium 134, but niobium 146, but tantalum 146, niobium, tantalum same. Here is a manganese, technetium and radium. Manganese 126, technetium 136, radium 137, almost same. Here you see nickel, platinum, palladium. Here you see 137 and 138. Okay. So in this way you can easily understand, okay, this thing. Next we will go for the ionic radii. Ionic radii also follow the same trend like atomic radii. But ionic radii of transition elements are different in different oxidation states. In general, ionic radii decreases with increase in the oxidation state. In the same oxidation state, ionic radii decreases with increase in the nuclear charge. Next we will go to the ionization energy or ionization enthalpy. The fast ionization enthalpy, okay, of the d block elements are higher than those of the s block elements, but lower than the p block element. And the ionization energy increases across series when we are going from left to right in a period, okay, but the increase is not the regular. If we look at here, then you can understand that scandium 631, then titanium increases 656, then vanadium 650, then again 652, then again changes to 717, then iron 762. These all are in kilojoule per mole. Then cobalt 756, this 736, then 745, then 906. Okay. In case of d block elements, the electrons enter into the n-1d subcell, and hence nuclear charge as well as spinning effect increases, and these two effects try to cancel each other, and that is why there is a small variation in the values of the ionization enthalpy. If you look at the zinc, cadmium, mercury, here you see that 906, 87, 1007. So in case of zinc, cadmium, mercury, they are very high ionization energy value, and they have stable electronic configuration. Okay, and second and third ionization series or ionization energy, second and third ionization enthalpies. Okay, if we look at the here, I have not written all. Okay, look at your book. Okay, then what you will see that the second and third ionization enthalpies increases with increase in the atomic number. Generally, with the exception of chromium and copper, which possesses larger values, okay, than those of their neighbors. This is due to the low shielding of the 4f orbitals and the fast ionization energies of the third transition series are higher than than those of the elements of the first and second transition series. Okay. Here data are not there. Okay. Now we'll tell about the oxidation state. With the exception of the few elements, most of the transition elements show variable oxidation state. Okay, due to nearly similar increase in the N-1d and NS subcells, except scandium. Okay, scandium in class C state. Okay, and other elements of the first transition series show +2 oxidation state. Okay, as the most common oxidation state in their compounds. Here some oxidation state I have written. Okay, scandium is showing that is the most common oxidation state. Scandium is showing +3, titanium +2, +3, +4, vanadium +2, +3, +4, +5, then chromium +2, +3, +6, manganese the +2, +3, +4, +6, +7, iron it is showing +2, +3, +4, +6, cobalt is showing +2, +3, +4, and nickel is +2, +3, +4, copper is showing +1, +2, and zinc generally +2. So element of transition series +2, +3 oxidation state forms ionic bonds, while elements with higher oxidation number form covalent bonds. And unlike p block elements, the higher oxidation states are more stable in heavier transition elements. The highest oxidation state is shown by transition element that will show here is not written +8. Okay, that will be shown by ruthenium and osmium. Okay, if you look at the periodic table, here it is there. Where is ruthenium? Here, just below iron, ruthenium and osmium. Okay, so they are showing +8. Okay, oxidation state. So the transition metals in their compounds formed with oxygen and fluorine shows higher oxidation state due to high electronegativity of oxygen and fluorine. Next, we will discuss about the formation of colored ions. Already I have discussed in complex compound or coordinate compound I have discussed. Okay, most of the transition metals compounds are colored in the solid form or in solution form. The color is due to DD transition. Okay, when a light falls in a compound of transition metal, okay, these electrons can be easily promoted, okay, from lower energy to higher energy by absorption of energy, light energy. Okay, and these and the rest color of the white light of transmitted and the compound appear colored. Okay, so whenever you are showing color, that means if white, why this is white? Because it is reflecting all the white light. Okay, it is coming. That is why it is white. And why your hair color is black? Because it is absorbing the all light. Okay, that means light condense. You know that basic 7 colors gives you. Okay, at least it is black. But in this case, okay, that whatever light is transmitted, that's after absorption, whatever left, the rest color, okay, will be transmitted, and you will be able to see that colors in the transition compound. And the observed color is always the complementary color of the color of the white light is absorbed. Okay, because of this DD transition. Next, we will discuss about the catalytic properties. Most of the transition metals and their compounds acts as a catalyst. Catalyst due to their tendency to form reaction intermediates with a suitable reactant. Okay, and their suitable surface where the reactants are absorbed, and they in this way they are coming close together, okay, one another, to promote the rate of reaction. Another, we can say that these metals have vacant d orbital and variable valency state or variable oxidation state. Okay, variable oxidation state, that is why they can be used as catalyst. And certain metals compounds provides low energy, that means I am telling about that activation energy, low energy path, okay, for the reaction by change of their oxidation state. Next, we will tell about the tendency to form complexes. These metals have availability of vacant d orbitals with suitable energy to accept lone pair of electrons donated by the ligands to form coordinate bonds and coordinate complexes. Okay. Another cause we can tell that small size of their atoms or ions or higher nuclear charge of their atoms or ions. Okay. So these are the cause, okay, of the formation of this complex compound. Okay. Next, we'll discuss the last general property, that is the magnetic property. All of you know that transition metals ions having unpaired electrons, and generally unpaired electrons are paramagnetic in nature, and if there is no unpaired electron, that will be diamagnetic in nature, and magnetic moment mu can be calculated by this equation. Mu is equal to root over n into n plus 2 Bohr magneton Bm. Okay, and n is the what? N is the number of unpaired electrons. Okay, so in this way we have completed the discussion of the D block elements, and in my next class we will discuss the A block elements. And if you have any confusion or any doubts, you will clear in your live class. So today up to this, thank you.